Hello. Today we're going to have a look at the second key area of the electricity unit in National 5 physics. We're going to be looking at the idea of voltage or potential difference, Ohm's law, and some circuit rules. So, first of all, we need to understand a little about electric fields. Now, any electric charge will have an electric field around about it, and an electric charge placed within an electric field will experience a force. We can draw electric field lines to show the direction that a positive charge would be forced to move if placed at a point in that field. So a positive charge would have the arrows pointing away in all directions because another positive charge would be forced away in all directions because it will be repelled. A negative charge will have the arrows pointing inwards because a negative charge will attract a positive charge from whichever direction. If we're interested in what would happen to a negative charge, all we need to do is think of it travelling in the opposite direction to which the arrow points. So a negative charge would be attracted towards the positive and away from the negative. Now, if we have what's called an electric dipole, so if we have two fixed positive charges, then we end up with a field pattern a little bit like this. So a positive charge would be pushed away from both charges. If we've got a dipole, two charges of opposite type, then any positive charge would be attracted towards the negative and repelled away from the positive at the same time. So we get a field pattern a little like this. We can also get two parallel charges. So in this case, the positive side and the negative side are two parallel metal plates opposite each other. And the field lines show lines pointing directly away from the positive and towards the negative. Now, this is a little bit like the gravitational field that we see on Earth. It's what we call a uniform field. So as we can see, the arrows are an equal distance apart throughout, which means that the field strength is the same wherever within that area. Now, if we have on Earth, we can imagine if we lift something up, it gains potential energy. And if we let go of it, then it falls and it loses that potential energy. Now, in an electric field, that's a little bit similar. So, in the picture of the man standing on the grass there, up high in the tree would be an area of high potential, and on the ground, an area of low potential. In the same way that at the positive plate of the charged plates on the left would be high potential, and the other side low potential. In between, therefore, we would have a difference in potential, or a potential difference. Now, in electricity, we call this potential difference a voltage. Okay, potential difference or voltage is known as the energy converted per unit of charge as it moves between 2 points or within a component. Now, that means that the volt, the unit of 1 volt, is equal to the unit of 1 joule per coulomb. Now, a good way to understand electrical movement, current, and potential difference is to think of our penguins on their little penguin race. So here, the penguins are like electrical charge, and you can see they climb up the steps, and then they slide down the slide, and they start again. Now, an electrical circuit works in a very similar way. We have the electrons traveling around the circuit. They pass through the battery, and then they travel around the circuit and back to the battery again. Now, the current. Electrical current is the rate of flow of charge. A little bit like the rate of flow of penguins. So how rapidly the penguins are moving around the circuit, how rapidly the charges are moving around the circuit. The potential difference, remember, is the energy gained or lost per unit of charge. So going around the circuit, the electric charges gain a particular amount of energy as they pass through the battery. So if we say it's a 1.5 volt battery, each coulomb of charge would gain 1.5 joules of electrical energy passing through the battery. And then as the electrons or the charges flow around the circuit, that energy gets used up. Now this is exactly the same as the penguins going up the ladder and down the slide. The penguins gain potential energy going up the ladder in the same way that the electrons gain electrical potential going through the battery. And then they slide down the slide and they lose that amount of electrical potential as they go around the circuit. So the battery is like the steps, the penguins are like the charges, and the slide is like the circuit itself. Whichever way we're looking at it, the potential in is the same as the potential out. So if we were to measure the amount of potential energy the penguins gain going up the steps, that's the same as the amount of potential energy they lose as they slide down the slide. In the same way, if we measured the voltage across the battery, the potential difference across the battery, the number of joules each coulomb of charge gains passing through the battery, that will be the same as the amount of energy lost by the charges as they go around the circuit. The voltage across the lamp in this case, the potential difference across the lamp, the number of joules of electrical energy converted to light or heat energy in the lamp would be the same as across the battery. So, another quantity within electricity that we need to understand is resistance. Resistance is the measure of how difficult it is for current to flow. And there are a number of things that affect resistance. The longer the wire, the higher the resistance. The further the electricity has to pass through a component, the more difficult it will be. The area of the wire that the electricity is passing through, the smaller the cross-sectional area, the less the current will be because of the higher the resistance. The material. Some conductors are better than others. The temperature. The higher the temperature, the higher the resistance. Or indeed, the lower the temperature, the lower the resistance. And in theory, if we could reach a temperature of 0 Kelvin, absolute zero, then the resistance of a metal would tend towards zero. It would be what we would call a superconductor, in that current could pass through it with no resistance. Now, these quantities, current, voltage, and resistance, are linked by a rule called Ohm's Law. And there's an experiment that we can use to verify Ohm's Law. And this little diagram here shows the experiment, the setup of the experiment that we would do. So we have a variable power supply connected to a resistor and an ammeter connected in series. Now the ammeter must be connected in series because it effectively counts the charges as it passes through it to work out the rate of flow of charge. And a voltmeter connected in parallel with the resistor. A voltmeter must be connected in parallel because it is trying to work out the difference in electrical potential. So it needs to know how much electrical energy the charges have at one side of the resistor and at the other, and compare them in order to work out the potential difference. So what we would do, we would set up the circuit, we would set the value of the variable power supply and measure the current through the resistor and the voltage across it. We'd alter the value of the variable power supply and repeat it. Then we're going to draw a graph of voltage against current and work out the gradient of the graph and compare this to the value of the resistor. Now, this is the graph that we drew, and the conclusion that we can draw from that is that voltage and current for this resistor are directly proportional. We can see that because it is a straight line passing through the origin. Now, I can also figure out the ratio of the voltage to the current, or indeed the gradient of this line. So, by dividing the voltage by the current value at any point, I can see, in this case I've divided 4 volts by 0.18 amps, I get a number of 22. And that happens to be the resistance of the resistor that was in the circuit. So that tells me that for a fixed value of resistor, the voltage and current are directly proportional, and the ratio of voltage to current is equal to the resistance. Now, the resistor is what's called an ohmic device, which means that the current and voltage are directly proportional to one another. We get other devices which are non-ohmic devices. For example, a filament lamp. What that means is the ratio of the voltage to the current is not fixed. Voltage divided by current will be equal to resistance, but that resistance changes. And in the case of a filament lamp, what happens is, as the current increases, the lamp gets hotter. As the lamp gets hotter, its resistance increases. And so changing the voltage and the current also change the resistance. So the two quantities are no longer directly proportional. Therefore, it is what we call a non-ohmic device. So this brings us to the Ohm's Law formula. V equals I times R. Voltage equals current times resistance. Here's an example. A battery supplies a lamp of resistance 10 ohms with a current of 0.2 amps. Calculate the voltage supplied by the battery. So we're going to take our formula, V equals I times R, 0.2 times 10, which is 2.0 volts. Now, looking at some circuit rules, finally. There are two types of electrical circuits that we deal with, series circuits and parallel circuits. So first of all, we're going to have a little look at current in a series circuit. Now, current in a series circuit is the same at all points because the same charge has to flow everywhere within the circuit. So if the current leaving the battery is 3 amps, the current all the way around the circuit will also be 3 amps. So we could write it like this. IS equals I1 equals I2 and so on. Voltage in a series circuit though splits up. It's shared between the components. So here we have a series circuit containing a cell and 3 lamps. And you can see the potential difference across the cell is 12 volts. But the potential difference across each of the 3 lamps is 4 volts. The reason for that is that, remember, voltage or potential difference is the energy per unit of charge. 12 volts, the supply voltage, tells me that each coulomb of charge gains 12 joules worth of energy as it passes through the battery. It's then going to lose that same 12 joules worth of energy as it goes round the circuit. Therefore, it cannot give all of its energy to one component. That energy is going to be shared. If the 3 components, in this case the lamps, are of equal size, then it will split equally 3 ways. If the lamps had different resistances, then we may have had the situation where we had 8 volts, 2 volts, and 2 volts. But the total voltage across each of the components in the circuit would have to still add up to the supply voltage. So the supply voltage is equal to the sum of the voltages across the components in the circuit. In a parallel circuit, things are a little different. When we think of current, the current will split as it goes around the circuit. A little bit like cars as they come to a junction in a road. Some cars will go one way and other cars will go the other way. An interesting way to think about this is if you cast your mind back to the penguins on the penguin race earlier, all the penguins went up the ladder and then they all slid down the slide. If it had been a parallel circuit, that might have been a little bit like at the swimming pool, where you go up a ladder and you get to the top, and there are a range of options of flumes to slide down. So you could go down the red flume, the green flume, or the yellow flume. All three flumes end you up in the same pool at the bottom, but they take a slightly different route to get there. So you can't go down all three flumes at once. You have to pick which flume you're going to go down. And a parallel circuit's a little bit like that. Each bit of charge has to pick which branch it's going to flow along. So if 18 amps were flowing from the battery, then that 18 amps is going to have to split three ways. And again, if the components have equal resistance, then the current through each branch will be the same. If one has a larger the resistance than the others, then less current will flow through it and more through the others. However, the current in a parallel circuit, the total current in a parallel circuit, will be equal to the sum of all the currents in each of the branches added together. Finally, voltage in a parallel circuit. In a parallel circuit, the voltage across each branch in the circuit is the same. Again, let's think about the idea of the penguins going up the ladder and then having options of different flumes to go round. Remember, the potential difference is the amount of energy gained or lost per unit of charge. So all the penguins climbing up the ladder gain the same amount of energy. Then all the penguins going down the slides lose the same amount of energy. But each penguin only goes down one slide. So each penguin gives all of their energy up on that slide. And it's the same situation in a parallel circuit. So each coulomb of charge here gains 12 joules worth of energy as it passes through the battery. The potential difference is 12 volts. Therefore, each coulomb of charge will have to lose 12 joules of energy passing through whichever loop it chooses to go round. Therefore, the potential difference across each of the branches will also be 12 volts. So, in a parallel circuit, the supply voltage is equal to the voltage in the first branch, which is equal to the second branch, and so on. So here's an example. Here we've got to work out the quantities on each of these meters. So first of all, we need to look at this and we see that the current flowing out of the battery is 3 amps. Therefore, the current in each of the ammeters will also be 3 amps because it's a series circuit. In a series circuit, the voltage, though, splits. So if the voltage across the supply is 12 volts and there are 3 resistors, then the voltage across each of the components will also be 4 volts. Here we've got a parallel circuit. So we can see the current leaving the battery is 3 amps. Indeed, the current returning to the battery will also be 3 amps because the same electrons, the same charges, will go all the way around the circuit. But in a parallel circuit, the current splits. So if each of these lamps are identical, the current is going to split equally 3 ways. So a third of the 12 volt, a third of the 3 amps will go each way. So the current through the top branch will be 1 amp. The voltage across each component in a parallel circuit is the same as the supply voltage though. So the voltage across the lamp will be 12. 1 amp, 12, 1 amp, 12 volts. Now, the last thing we need to look at are resistors in series and parallel circuits. So in a series circuit, if we have a number of resistances connected together in series, it's very easy to work out the total resistance because the total resistance just increases the more resistors there are. So the total resistance in a series circuit is equal to the sum of each of the resistor values within the circuit. So for example, here we've got a circuit with two 10 ohm resistors and a 20 ohm resistor, so we can work out the total resistance by adding up the resistors R1, R2 and R3, and we get 10 plus 20 plus 10, which is 40 ohms. Resistors in parallel are harder to deal with though, because in a parallel circuit, remember, the current has a choice about going down different branches. So the more branches we add, the more easy the current will flow. It's a little bit like if you've got a single track road, you get lots of traffic jams because all the traffic gets all bunched up. If you expand it and make it a dual carriageway with 2 lanes of traffic, then the traffic moves a little bit more freely. If you expand it and make it a 3-lane road, the traffic will move a little bit more freely still on a motorway. And a parallel circuit's a bit like that. So the more branches we have in a parallel circuit, the smaller the overall resistance becomes. So we've got to calculate the total resistance using this formula arrangement, where we deal with fractions. Now, it's a little bit cumbersome to deal with, but here's a procedure to go through to work it out. Firstly, look at your calculator, and hopefully you'll find on your calculator there's a button that says either x to the power minus 1 or 1/x. It's there on this Casio version. It'll depend on the make of calculator, what it actually says and where it actually is. But that's the button that we're going to use here. Now, here's how we're going to work it out. We've got a 100, a 200 and a 100 ohm resistor connected in parallel. So, when we do this sort of thing, if we're asked this question, we're going to write down, like we would usually do with any calculation, we're going to write down the formula first. So 3 resistors in parallel, I do 1 divided by the total resistance is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. I then put the numbers into the formula. 1 divided by RT equals 1 divided by 100 plus 1 divided by 200 plus 1 divided by 100. However, at this point, I then type into my calculator 100 x to the power minus 1 plus 200 x to the power minus 1 plus 100 x to the power minus 1 equals a little bit like this. And that gives me a value of 1 over 40. So 1 over the total resistance is 1 over 40. I then need to press x to the power minus 1 again, equals, and that gives me my final answer of 40 ohms. So watch the calculator again. I typed 100 x to the power minus 1, so that's 1 over 100, plus 200 x to the power minus 1, that's 1 over 200, plus 100 x to the power minus 1, that's 1 over 100, equals, so that's my 1 over total resistance is 1 over 40. I then press 1 over x again, equals, and I get my final total resistance value. And you can see here the total resistance value in a parallel circuit of 40 ohms will always be smaller than any of the individual resistances within the circuit. Okay, so I hope you found this video useful. Next time, we're going to have a look at some practical circuits, looking at LEDs, thermistors, LDRs, and transistor circuits. But until then, bye for now.